So in this video, we're going to take a closer look at logarithms, specifically asking if, we can consider them as functions and exploring them as functions. There is a video lesson notes and example sheet that might be a good way to take notes in this video. So we'll just start off here with number one. Assuming you watch the video on exponential functions, you should be able to sketch a pretty accurate graph of y equals 2dx over here on this graph paper. I'll remind you that there are three main features we kind of talked about, two of them being particular points that you could use, and then there's also an asymptote on this graph. So why don't you pause the video and see if you can sketch the graph of y equal 2 to the x. Probably even just making a table would help. Okay, see if this is what you did. So previously we had talked about how the points 0a and 1a times b are on the graph. In this case, our a is just 1. So we would have the point 0, 1, right? If we put 0 in for x, we get back 1, and then the point 1, 2 on the graph. And then the third feature that we talked about was the horizontal asymptote of y equals 0. Now, we could also maybe graph a few more points, but let's go ahead and put these in here. So we have 0, 1, and then 1, 2, and then here's that horizontal asymptote of y equals 0. So we can already tell that the graph is generally just going to kind of come up doing that, go through those 2 points. Let me undo that. But let's pick a couple more points while we're at it. So if we were plugging 3, oh, I'm sorry, if we were plugging 2, let's do 2 first, right? We would just have 2 squared, so we get back 4. If we plug in 3, we'd have 2 cubes, so we get back 8. And then let's go a little bit to the left of the y-axis. If we plug in -1, right, that would be 2 to the -1, which we recall is just 1 over 2, right? So we're going to have this point -1, 1/2, right? We're going to have 2, 4, and we're going to have 3, 8. And this is more than enough information, I think, to be able to sketch this graph. Okay, so now that we have an accurate graph of y equals 2 to the x, let's turn our attention to sketching the graph with its inverse here in number 2. And we'll just do it right on this set of axes. Hopefully when you see that word inverse, you're already thinking that we need to switch blank and blank for each point. What are we talking about here? So hopefully you're thinking like input and output, or x and y. We want to switch the x and y for each point. If you do that, you will have the inverse. That's what inverse is all about, is switching the input and the output, or the domain and range, or the x's and the y's. So when we get done, we have a way that we can kind of check our graph. But why don't you pause the video and see what you can do with that. Well, now if you switched all the x's and y's, we just need to plot these points here, right? 1, 0, 2, 1, 4, 2, 8, 3. So I've done that here, and I even plotted 1/2, -1. And so that gives us a pretty clear picture of what this inverse is doing. There's one more feature, though, that I haven't included, and that comes up here. If we have a horizontal asymptote of y equals 0 on the original graph, then hopefully you were thinking, yes, we need a vertical asymptote of x equals 0, right? The x and the y just get switched. All right, so let me put that in and see if I can sketch that graph. All right, well, I didn't do a great job with the vertical asymptote on this graph, but I hit most of the points in it. Hopefully this is what the graph of your inverse is looking like. And we can see that if we look at the two graphs together, there is this symmetry with the line y equals x. So I drew that in so you can kind of see the symmetry there, and that's what should happen anytime that you sketch an inverse of a function where you're switching the x's and the y's. All right, what I'd like to do now is take a look at, well, just kind of check this out using the calculator. All right, let me open a new file, and we'll add graphs. And before we actually graph y equals 2 to the x, I'm going to change this up. You've seen me do this in class. I'm going to change the entry edit up into parametric. This is that mode where you can define the x and the y separately using a third variable, which is t. So if I want the graph of y equals 2 to the x, I can just let x be t, and then I'll do y equals 2, use the caret, y equals 2 to the t. So this should give me y equals 2 to the x. Now I do need to change some of the entry things I have down here. Let's go from -10 to +10. And step, we'll just say 0.1. Not that that really matters. But there's our graph of y equals 2 to the x. Can bring it in a little bit so we get more of the graph that we saw. Okay, and now if we want the inverse of that graph, I'm going to go hit the tab button, and I'm just going to switch the x and the y, right? So we can let the x now be 2 raised to the t, and we can let the y just be t. And let me go ahead and change this over, make that a 10, it's a -10. There we have our inverse graph, right? And we can still see that symmetry. Could even graph the line y equals x. That's right, I need to be in terms of t. So let both things be t. There we go. And we see that symmetry. So now that we've handled getting the inverse of the exponential graph, let's get the actual formula here. So you probably have done enough in the last couple of videos to be able to get the inverse of this function y equals 2 to the x, get the formula for it. As it mentions, we might need to think back to how we used to get inverses earlier in the year. But you basically need to switch the x and the y, but not so much literally switch them, but switch their roles. We now want the y to be the input variable and the x to be the output variable. That's essentially what we need. So that means we basically want to solve this equation for x, all right? So use what you know about solving exponential equations to do that. Pause the video and try it. All right, is this what you got? All right, so now if we need to solve for x up here, that's the variables in the exponent, we definitely need to use a log to do that, right? And you may not have written this second line, and I'm fine with that. Many students would just go straight from this first line down to this third line. They're just going to change the exponent to a log using the definition of a logarithm. So we need our base to be 2. We're going to take the log of the power, right? In this case, the power is y, and that's going to equal the exponent, which is x, right? So, you can almost think of this top line and this third line as kind of equivalent equations, equivalent expressions. They're just written in a different way. But the middle line kind of shows algebraically what you're doing. You're actually taking the log base 2 of both sides of this equation. And on the right-hand side, the log base 2 will cancel out with the exponential 2 to the x, just leaving with the x, all right? Because as we were talking earlier, we have an inverse situation here. All right. Now, if we were just to graph this log base 2 of y equals x, notice that the y is the input variable and the x is the output, and that's what we wanted. We wanted them to switch their roles. But if we were to actually graph them, the x would be on the vertical and the y would be on the horizontal, and we would get, and we would be graphing that way. If we're going to graph this on the calculator, we need to actually switch, okay, the x and the y, because the x is always the input variable on the calculator, and the y is always the output, right? They always have the y on the vertical and the x on the horizontal. So we're gonna actually literally switch the x and y so that now when we go back to our calculator, we can kind of check our graph here and get some of this stuff out of the way. I'm going to go back to menu, graph entry edit, and change back into function mode, all right? And let's graph the we'll basically have y equals here, and I'm going to hit Control and then 10 to the x. That brings up the log thing, and we have a base 2 here, and we're going to plug in x right there. And what we should get, I'm not sure what color we're going to get. I might change the color here, but we should get something that looks familiar. Yes, you can see. So I just had the blue graph. Let's change that color. Let's make this green, so we have different colors here. But now we see that that new green graph is actually right on top of the red graph. So we actually have found the formula for the inverse graph of the exponential to the x. And we can kind of, let's see if I hit tab and go back and forth between these two graphs and see that they do appear to be right on top of each other. Okay, so we have a definition here for the logarithmic function, okay? Not only have we seen that the log is the inverse of the exponential, the graphs match, but also we can see from the graph here on the calculator that it does appear to be a function, right? There's only going to be one output value for every input. We're passing the vertical line test. So this definition actually should look fairly familiar. We've already kind of defined what a log is when it comes to solving an exponential equation. So we're still going to have that as long that x needs to be positive, the base needs to be positive, and the base also should not equal 1. And if that's the case, then y equals log of x base b is called a logarithmic function with base b. All right. And of course, we write it this way. Let's just go ahead and point out that it is the inverse function of y equals b to the x. And let's remind ourselves here that what we're taking the log of, right, is the power, and what we're getting back is the exponent. Okay. Over here, of course, when we're in an exponential situation, we have the base raised to the exponent equals the power, and here the output now is the exponent while the input is the power in the log.